Hello, I'm Seema and welcome to part 10 of the chapter Thermodynamics. It is now time to introduce a new state function, the name of which is enthalpy. It is represented by H and it is known as the heat content of a system. So let me just remind you what a state function is. A state function is a property on which the state of a system depends. For any state, that property is fixed, or the magnitude of that property is fixed for a certain state. And if you move from one state to the other, since that quantity at both the states is fixed, irrespective of what your path is, when you move from A to point B, then whatever the change in that quantity has to occur would be the same, irrespective of what your path is, whether it went up, came down, moved another path and then came from A to B, or it went straight from A to B, the change that occurs would be the same. Such a function is known as a state function. And this property that I'm going to introduce, that is enthalpy, that is also a state function, right? So we just need to know right now what state functions are, and then let us now start studying about enthalpy. In the previous videos, I told you about the first law of thermodynamics. And what was the equation of the first law? The equation was delta U, that is the internal change in internal energy, is equal to the change in heat, the amount of heat, minus the work done. Or rather, plus the work done. And for work, we use the expression minus P delta V. So delta U is equal to Q plus W. That is the equation, the mathematical form of the first law of thermodynamics. And the W becomes minus P delta V. So the first law of thermodynamics, the equation becomes delta U is equal to Q minus P delta V. Also, we had studied that when volume is constant, if volume is constant, delta V becomes zero. That is, change in volume becomes zero because volume is constant. So if delta V is zero, P delta V becomes zero. Which means now for an equation, for a change where the volume is constant, the change in internal energy becomes equal to only the change in heat content. And that is the amount of heat exchanged. So delta U becomes equal to Q, and we use the subscript V. The reason that we just want to specify that this is the change in heat which occurred at constant volume. So QV is delta U is the change in internal energy, and QV is the amount of heat that was exchanged to cause that change in internal energy at constant volume. This is what we have studied in the previous videos. Now let us move. Most of the reactions that occur, whether we are carrying them out in laboratories, or we are carrying out changes in industries, or they are just changes occurring in nature, we do not have fixed volumes. We don't have reactions occurring in closed boxes where we do not allow the thing to expand or contract. The expansion and contraction or change in volume is a common thing. The one thing that is actually constant would be the atmosphere and the pressure, that is the atmospheric pressure. So the system is, or what is the system? That part which is undergoing change and which is your area of focus. Around it, it is being surrounded by the atmosphere which has its own pressure. So usually we carry out more changes at constant pressure instead of constant volume. So, if we assume that the change is occurring at constant pressure and not constant volume, then P delta V would be as it is, but this time we would like to specify that the heat which is changing is at constant pressure, so we use the subscript QP in this case. It is the same equation, only by writing this P we have specified that this change is occurring at constant pressure. Clear? After this, if this is a change that is occurring at constant pressure, and let us assume that we are focusing on the change. Delta U is the change in internal energy. It means that if the change is occurring from step A to step B, or state 1 to state 2, then state 1 is the initial state and state 2 is the final state. Let us assume that these are the two states, 1 and 2. If state 1 and state 2 are the initial and final states, then what would delta U be? the internal energies at these two states would be U1 and U2, and delta V means it has two volumes, that is V1 and V2. So we say, if we try to substitute these values to show the deltas, we would say that U2 minus U1, that is the change in internal energy, final internal energy minus initial internal energy would give you delta U, would be equal to QP, we keep the equation as such, minus P remains there, into V2 minus V1, the change in volume. Now, if we rearrange this equation, what are we doing? We'll take QP to this side and we'll bring the U1, U2 to the other side. When we do this, QP comes here, so QP becomes equal to U2, or rather let me say I'm bringing this entire part here and keeping QP where it is. So U2 plus PV2. Do you see? The sign of PV2 would change when it comes this side. PV2 and PV1. We could write this as QP minus PV2 minus PV1, right? So when we take all of this to that side, QP would become equal to U2, and we are putting the two 2's together and the 1 1's together. So we get QP is equal to U2 plus PV2 and minus U1 plus PV1, right? So we have arranged it in such a manner that you get these two values, U2 plus PV2 and U1 plus PV1. This is the quantity, that is U plus PV, which was called enthalpy. Right? When we said what was internal energy? Internal energy was the sum of exchange of heat and the work done. And what was H, this enthalpy? Enthalpy was said to be equal to the sum of the internal energy and work. It was the sum of the change in internal energy or internal energy and work done. So this quantity was introduced as the new state function that I'm introducing here, which is known as enthalpy or heat content. So H is equal to U plus PV. Also, I told you that I'm introducing a state function. Why are we calling it a state function? Why is it independent of path? Why does it not depend on the path of the reaction that you are following? I'll tell you that. Heat Q is dependent on path. It is not a state function. The heat that is absorbed or given out, it depends on the path. So it is not a state function. So if you have something which is not a state function in an equation, then the other things, the entire system or that property should not be a state function. But what do we notice here? That although Q by itself is not a state function, internal energy we know is a state function, pressure, volume, temperature, we already know are state functions. We did in the states of matter that the gaseous state depends on the pressure, volume, temperature and number of moles. So pressure and volume are already state functions. Internal energy as a state function we've already studied in the previous videos. So QP, although Q is not a state function, QP is depending on state functions completely. All of its magnitude depends on the state functions, and therefore QP also becomes a state function. Since it depends on state functions, QP also becomes a state function, and QP is actually, what is it? It is the change. Now if you look at this, H, that is enthalpy, is U plus PV. So if you have U2 plus PV2, it means enthalpy. What enthalpy would this be? This would be enthalpy of the state 2. So it would be H2. And U1 plus PV1, since H is U plus PV, U1 plus PV1 would show you that is H1. H1 would be U1 plus PV1. In other words, we can write this equation as QP is equal to H2 minus H1, and the change in enthalpies would be shown by delta H, which is a change in enthalpy. Is it clear till now? Now, QP therefore is equal to H2 minus H1, which is equal to delta H, which is the change in enthalpy. Now we are going back again. We know that QP here, this is the equation, that delta U was equal to QP minus P delta V. So we can rearrange this equation and write QP then would be equal to delta U plus P delta V, right? We just rearranged this equation. So QP at constant pressure, QP is equal to delta U plus P delta V. Also, we have just found out that QP is equal to delta H, right? We also just now found out that QP is equal to delta H. So QP is equal to delta U plus P delta V, and QP is also equal to delta H, which means that delta H is also equal to delta U plus P delta V, right? So we say, therefore we can write that delta H is equal to delta U plus P delta V. A is equal to B, and B and C is also equal to A. So C would be equal to B, wouldn't it be? I'm just trying to explain it. I'm sure you would have understood already. So we come to the conclusion that delta H, that is change in enthalpy, is equal to the change in internal energy and the change in the amount of work done or by the system or on the system. Now, whatever this state function delta H is, or the heat content, for an exothermic reaction, exo means exiting, going out. A reaction from which heat goes out is known as an exothermic reaction. A reaction that loses energy is an exothermic reaction. And a reaction in which something comes indoors, endo, come on endo, come indoors. So a reaction which is endothermic means a reaction in which heat is entering. And an exothermic reaction is where heat is exiting, it is going out. So when we say that enthalpy is the heat content, then for any reaction where heat is being given out, the amount of heat is being lost by the system. Therefore, delta H should be negative. Since it is the heat content, you remember we talked in the terms of work and internal energy, and heat, if heat is absorbed, then Q is positive. Why? Because Q is the heat of the system is increasing, and if heat is lost, then Q is negative. Why? Because the energy of the heat of the system is decreasing. The same logic we use if the reaction is exothermic, heat is going out, therefore delta H should be negative. If the reaction is endothermic, it is gaining energy, therefore delta H would be positive. And for all numerical problems, we should keep the signs always in mind. So moving ahead now, we had also said that at constant volume, this is where we started, that at constant volume, delta U would be equal to QV, right? We said that at constant volume, delta U, that is change in internal energy, is equal to QV. Why? Because at constant volume, there is no work done. Because delta V is 0 and therefore P delta V is 0, and you get delta U is equal to QV. And this equation 3, what does it become? Now look here, delta U is equal to QV. And what do we have in equation 3? It says delta H is equal to delta U plus P delta V. So, when volume is constant, P delta V is 0. So, what delta H would become equal to delta U? If we carry out this reaction at constant volume, what would happen? P delta V would again become 0. So, delta H would be equal to delta U. And we already know for reactions where the volume is constant, delta U is equal to QV. Therefore, for such reactions where volume is constant, delta H should be equal to delta U and it should be equal to QV. It means that change in internal energy and the change in enthalpy mean the same thing if the volume is the same. If the volume is the same, then there is actually no difference, no practical difference between delta H and delta U. And when is this important? In the previous chapter where we did the states of matter, I told you that gases are compressible. A change in a volume of gas is very easy, but liquids and solids are almost non-compressible. Their molecules are so closely packed that they are non-compressible. They cannot be compressed. And if liquids and solids cannot be compressed or expanded, their volume is virtually delta V in the cases of liquid and solid reactions would be 0. Therefore, for solids and liquids, the changes that are taking place in solids and liquids, delta H and delta U are equal to QV. They mean the same thing because there is virtually no difference in their volume. But when you talk of reactions that are gaseous, there the volume changes are significant, and therefore at that point you must keep in mind that delta H and delta U, they are not just the P delta V part of the equation also becomes important. For gases, in other words, the delta H is not equal to delta U exactly, because the work part or the change in volume also has to be taken into consideration. So we say delta H is equal to delta U for solids and liquids, but volume change is significant for gases. Now let us assume that there is a gas A, which is a reactant. We have a gaseous reactant A, and the reaction takes place and gives us the product B, and the product B is also gaseous, right? And both of these are ideal gases. The reactant A and the product B, both of them are gases and they are ideal gases. So let us see what happens when you have ideal gases and gaseous reactants and products. What happens to these equations? We know the ideal gas equation. If you do not remember the ideal gas equation, I would refer you to the previous chapter, that is the states of matter. And please watch those videos, and we did the ideal gas equation there, and the ideal gas equation is PV is equal to nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas, R is the gas constant, and T, capital T, is the temperature in Kelvin. Remember one thing. Whenever you are faced with temperature with a capital T, the capital should start ringing bells in your head. It should start ringing bells. Why? Because the moment you get the capital T, it means they are expecting you to report the temperature in Kelvin, right? Wherever you see temperature in capital T, it means they're talking of Kelvin temperature. If the temperature is also represented by a small t. So when it's a small t, it would be Celsius, it would be any other scale, the Fahrenheit, but if it's a capital T, then it means it is temperature in Kelvin, which is also called the absolute temperature. Just so you know, because we'll be doing a numerical where you'll have to keep this in mind. So according to the ideal gas equation, PV is equal to nRT. So if we apply this ideal gas equation for both the gaseous reactant and the gaseous product, we would get PVA, PV of pressure. Now this is taking place at constant pressure and constant temperature, right? This reaction is taking place at constant pressure and constant temperature. So T and P will be the same. So P, what is different than volume of A, will be equal to number of moles of A. R is a constant as it is, so RT. PVA is equal to NART, and for B we will write PVB is equal to NBRT. We number these equations as 4 and 5. I have circled all the numbers of the equations with red marks so that you don't get confused. It's not a part of the equation. So now if we number these as 4 and 5, PVA is equal to NART and PVB is equal to NBRT. Let us subtract 4 from 5. So we'll get PVB minus PVA would be equal to NBRT minus NART. Now take the common things which are the same here. P is common here, so keep it outside the bracket. VB minus VA would be equal to what is common here? NB and NART are common, so keep the RT outside the bracket and take NB minus NA. We know whenever we get final volume minus initial volume would be delta V. Final number of moles minus initial number of moles would give you the change in number of moles in the reaction. So that will give you delta N. and the G is for the gaseous state. This equation is only applicable when the reaction is taking place for gaseous reactants and gaseous products. It is only applicable when the reactants and products are gaseous and they are ideal, because we are using the ideal gas equation. So P delta V will be equal to delta Ng RT. And this is the equation that is used to calculate the change in enthalpy from the internal energy and vice versa, which you would do further in numerical problems. So now I would like to solve a couple of numerical problems here, and before winding up this video. Give me a moment so that I change everything on the board. Okay. So now this is question 6.5. It's a solved example of your textbook, but it will help you understand enthalpy better. And we'll solve other problems of enthalpy when we study enthalpy a bit better and we study different types of enthalpies. That is when I'd like to solve those numericals. But at this stage, just doing this couple of problems would be enough for the time being. Let us just read what the question is. If water vapor is assumed to be a perfect gas, when he says perfect gas, it means we're talking of an ideal gas. And therefore, we would be using this last equation that we just did. So, molar enthalpy, if water vapor is assumed to be an ideal gas or perfect gas, molar enthalpy change, that is delta H. For vaporization of 1 mole of water, it means what is happening? Liquid water is turning into gas, it is vaporizing. Of 1 mole of water at 1 bar, what is 1 bar? 1 bar is the pressure. At 100 degrees Celsius is 41 kilojoules per mole. You have to calculate the internal energy change when 1 mole of water is vaporized at 1 bar pressure and 100 degrees Celsius. Let us first write down what all do we have and what is the equation that we would be using. Let me first just write down the equation that we are going to be using. The equation that we are solving part 1 now. The equation that we just did was that delta H is equal to delta U plus delta NGRT. Remember, delta H is change in enthalpy, delta U is change in internal energy, delta N is the change in number of moles, R is the gas constant, and T, I told you, why did I tell you about the capital T? That when we're talking of capital T, it should always be in Kelvin. And look at this, what have they given us? 100 degrees Celsius. They've given us the temperature in Celsius. So that's why I told you, the moment you see a capital T, it should start ringing bells in your head that you're supposed to convert the temperature, or at least make sure that the temperature is in Kelvin. So let us see what are the quantities given to us. If water vapor is assumed to be a perfect gas, molar enthalpy change for vaporization of 1 mole. So number of moles is equal to 1. Right? 1 mole of water at 1 bar and 100 degrees Celsius. Now, what's the 1 bar pressure is equal to 1 bar, right? And what does it tell you more? And temperature. Temperature is 100 degrees Celsius and we want to convert it to Kelvin. So it will be 373 because you have to add 273 to any degree Celsius to convert it to Kelvin. So this would be 373 Kelvin. And the molar enthalpy means it is delta H. Delta H is given to us is equal to 41 kilojoules per mole. Right? When the delta H given to you is in kilojoules per mole, you know, the value of R depends on the units that you're using for the other state functions. So whatever you're using for pressure, whatever you're using for volume. So in this case, you get this in joules. So you have to use the value of R which has joules in it. So joules, mole, Kelvin. These are the units that we are using otherwise. So we will choose that value of R which is in joules per mole per Kelvin, and that is, therefore for this case we will be using R as 8.3 joules per mole per Kelvin. Now what is the change that is occurring? 1 mole of water, now we have H2O liquid, 1 mole, is vaporized at 1 bar pressure and 100 degrees Celsius. It turns into H2O gas, right? This is what is happening. This is the change that is occurring. what are we supposed to do? We have to find out, calculate the internal energy change. Calculate the internal energy. So we have to calculate delta U. Delta H is equal to delta U plus delta Ng RT. Rearrange this. We are looking for delta U. So delta U would be equal to delta H minus delta Ng RT. Now substitute the values. We have them. Delta U would be equal to, what is delta H? Is 41. Write down the units, 41 kilojoules per mole. Right? Minus, what is delta N? Number of moles, it is 1. So it remains 1. And R into R is 8.3 joules per mole per Kelvin, right? And the temperature should be in Kelvin. What is the temperature? It was 100 degrees Celsius, that is 373 Kelvin, right? So now when you find the sum of this, this would be equal to 41 kilojoules per mole minus, now you have kilojoules here, and what you'll be calculating here, we have joules per mole. And Kelvin, inverse and Kelvin, they get cancelled. So you should get, whatever quantity you get here should also be in kilojoules per mole. So we get, the quantity that we get here would be 3096 joules per mole, right? But we need kilojoules. So we'll write this will be equal to 41 kilojoules per mole minus 3.096 kilojoules per mole. Right? Now you can carry out this subtraction and the value you get would be equal to 37.904 kilojoules per mole. That's your answer. You get this? Now what is the second part of the question? The second part says that 1 mole of water is converted into ice. Now the change of state is occurring from the liquid state to the solid state. So if that is happening, the delta V is constant. So the delta NGRT, this part would not be important. You remember? And delta H would be equal to delta U. So when he says that 1 mole of water, now second part, 1 mole of water, that is a liquid, is getting converted into water, that is ice, solid. And then he says, well, you have to find out the change in internal energy. In this case, delta NGRT would be equal to delta NGRT would be equal to 0, as P delta V is equal to 0. And we know in place of P delta V, we had put the delta NGRT. For gases, and since we do not have the gaseous state, we have the liquid and the solid state, change in volume is negligible, almost equal to 0. Therefore, it is not significant anymore, and therefore, delta U in this case would be equal to delta H, which is already given to us, that is 41 kilojoules per mole. That's the answer. So this was enthalpy. If you found the video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.